Thank you very much. So now we have the second invited speaker. So it's my honor to introduce Dr. Charles Lesire. Charles Lesire is a senior researcher at AREA, the French aerospace lab, in the Department of Information Processing and Systems, where he leads the safe, embedded, and autonomous systems team located in Toulouse, France. Charles received his master's degree in computer science and aerospace engineering from INAC, École Nationale de l'Aviation Civile, and at the University of Toulouse, France in 2003, and his PhD in computer science from University of Toulouse in 2006. Since 2008, Charles has been a research fellow at AREA, working on robotics and autonomous systems. He's a IEEE Robotics and Automation Society member, and since 2019, he has also been an associated researcher of the Toulouse AI Institute. His research focuses on applying AI-based decision-making to autonomous multi-robot systems and on verification of autonomous systems behaviors. So thank you very much, Charles.
Okay, so thanks for the kind introduction, and I would like to thank the organizers for having invited me to do this talk today. So I will start with a couple of slides presenting just the lab where I'm working, and then I will detail some work we've done on multi-robot systems and how we can deploy multi-robot systems in outdoor fields, and the kind of architecture we developed that uses hierarchical and automated planning for the computation of plans and management of robots. So I'm working at AREA, so it's a national research center, which is specialized in aerospace engineering, and which is under administrative supervision of the Ministry of Defense. So of course we have a lot of defense applications, but we are also involved in a lot of works with industry from aeronautics, so from civil aviation, for instance. And there are a lot of topics covered at AREA, including the physics of waves, for example, and the building of specific sensors for applications, for aircraft applications, and also some topics on aerodynamics and the study of fluid mechanics and materials. The department where I work is more focused on information processing, so it's kind of merging of people coming from computer engineering, software engineering, and electric engineering. We have a lot of applications, specifically towards the certification of aerospace systems in civil aviation specifically. And also we work on the study of novel structures and concepts for aeronautic systems. And the topic in which I am the more involved is of course autonomous systems. So I lead a small team of 10 people in Toulouse, where we are really focused on autonomous robotics and also on embedded platforms, and especially new kind of multi-core embedded platforms for autonomous systems. And we use a lot of formal methods, both for the autonomy part in robotics and for the embedded systems. Today I will not speak a lot about formal methods, but more about how we give autonomy to robotic systems through the study of multi-robot system projects that we have conducted in my lab. So the main kind of applications we have are applications for defense, and they consist in deploying multi-robot systems for several kind of applications, like the surveillance of hazardous or unknown areas, search and rescue operations, and protection also. So protection missions are very common in this kind of projects, because often they use robots more to ensure some kind of permanent surveillance of or permanent protection of the area where the army is located, and it's a quite boring job, and where there is not so much need for human intervention when you use robots. And in all these missions, of course, you always have a human, or at least one, but maybe more, a human that supervise the mission, that must both understand what the robots are doing and also being able to intervene in the mission. When you have to deploy a multi-robot system in this kind of applications, there are several topics you have to consider, several challenges you have to consider. So first, we are trying to do is to develop some multi-robot task allocation algorithms, and they must take into account the specificities of the robots you have, so the specificities of the motion capacities, for example. So you have ground and air vehicles in most of the scenarios that we deal with. Some vehicles can only go on roads, others can go all terrains, or depending on the kind of terrain they have to go through. There are several sensors that can be used either to take pictures or detect intruders or other kind of applications. So you have to do this allocation in a sound way so that you allocate. You can try to allocate optimally depending on the capacities and the sensor of the robots. We have to manage a lot of synchronizations between the tasks, so because there are some dependencies between the tasks. So for example, in this kind of mission, we ask some of the robots to go to the border and protect the border of the zone before deploying other robots inside the zone to observe the buildings, for example. So we have to manage the synchronization of the tasks, both in the planning, so initial planning part, but also at execution, depending on the failures or new information that may arrive. We have some temporal constraints in the task achievement, like for example, deploy the robots for protecting the borders within the 10 next minutes, for example. This kind of temporal constraints with hard time constraints. And of course, as in main real robotic application, we have to manage all the things that will happen at execution, like failures, events, or new objectives, or new detections. The need to adapt the plan to what happens at execution. And another specificity is that in outdoor fields, you have to manage communication uncertainties. So you may have some communication failures. So for example, one of the communication antenna is broken. So you have to manage the fact that in some area you cannot communicate anymore, or the fact that one robot is too far from the others to be able to communicate with them. So we have to manage this communication uncertainty at execution. And as I said before, there is always an operator that supervises the mission. So it both needs feedback from what the robots are doing, and also it can modify or add new tasks to the robotic system. In the first projects we've done in this sense, we developed an architecture based on a hierarchical task network, which is a planning paradigms, where you decompose abstract tasks into more primitive tasks, primitive actions to perform a mission. So that's a quite common planning paradigm now. And what we've proposed is to use this planning paradigm in a distributed architecture so that we can execute the plans coming from the HTN planning algorithm in a distributed way among the robots. So each robot is responsible of executing its own part of the plan. And also we define some repairing procedures. And in these procedures, we specifically use HTN to model how to recover communications when you lose the communication with the user robots. And we applied this to RC scenarios, so it's a bit different from the previous picture, where a boat, an autonomous boat, an autonomous submarine, and a drone had to cover an area to detect a leakage from a wreck. Now we have, so the idea was to really use this hierarchical decomposition in the mission process, because it's quite natural for operators and humans to describe their mission in a hierarchical way. So we keep this hierarchical, the idea of having this hierarchical decomposition in the planning and in the decision making, and we elaborate around this to have some more complex and modern approaches of planning. So I will try to share a small video right now. To show you the, where we have, do you see the complete movie?
Yeah, I see.
Okay. So we have made an experiment with 8 robots a few years ago. that had to cover an area. So I will just pause here. So the objective was, so we have all these robots here, which are either ground robots or aerial robots. And we have in this area a set of points of interest. So the operator could select some points if want to observe. And then we have to allocate the observations to all the robots so that we can have in a given deadline all the points observed. Then, so we use a planner to first build the plan. So we allocate the path to go to the points of interest and the points and the observation of the points of interest to the several robots. So that's the initial plan of the system. And then the plan is executed by the robot, and during execution, the robot exchanges some information, and you can see that the communication graph, which is in green here, is local. So we cannot communicate with all the robots at every time, and we have only local communications. And during these local communications, the robots exchange some information about the delays they have in achieving their plan. And based on this delay, we will be able to adapt the schedule. So here you have for each line is a robot, and you have the schedule plan for each robot. And they adapt their schedule to the delays in order to still be able to execute the initial plan. And if there is a failure, so not just a delay, but a failure, so we simulated this failure with having to recharge an aerial robot, for example, then the tasks that have not been achieved by the robots will be reallocated. So we repair the plan by trying to find a new way to allocate the tasks that have not been done by the robot. So I will go back to the slides. Okay. So that was an experiment we conducted a few years ago in a specific military camp close to Toulouse. And what we have developed in this architecture, so to achieve this experiment, we developed several things. So first, we've made some task allocation and planning. So it's not just task allocation, it's also a planning at the same time. So at the same time that we allocate the tasks, we decide how to achieve them and how to schedule the actions of the robot to achieve the tasks. Using a planner we have developed, which is called HIPOP, and I will detail this just after. During the execution, as we've seen in the movie, we manage temporal execution with delays using so the framework of multi-agent simple temporal networks, and we propose the specific distributed propagation algorithms that allows to adapt the time constraints of the plan, even if you have some partial communication. So the robots are able to adapt the plan to the delays, even if they receive only a part of the time of the delays taken by other robots. And we also so used again the HIPOP algorithm to implement a repairing strategy. So the idea is to be able to repair the plan in case of failures. But when we repair the plan, maybe we cannot communicate with all the team, but just with a small part of the team. And the question is how to be able to repair the plan just for this subteam and keep the plan consistent for all the multi-robot system. So today I will not detail the distributed propagation on multi-agent simple temporal networks. I will just focus on the automated planning and repair parts. So we have developed an algorithm which falls in the hybrid planning paradigm. So hybrid planning is a specific paradigm that combines hierarchical decomposition, just like it's done in hierarchical task networks, with partial order planning. So partial order planning, which is also called partial order causal link planning or plan space planning, is a specific way to solve a planning problem where so in classical planning problem, when you solve the problem, you consider a graph where you know that are states of the system, like the position of the robots, for example, and the transitions in this graph are the actions that you can ask the robot to do, like move the robot or take a picture or these kind of things. And then you have a goal state to reach. In POP planning, the graph in which you make the search uses nodes which are plans. So it means that you have a plan, and that's the state of a node of your search graph, and you can do transitions on this graph, which are modifications of the plan. So you will modify the plan by adding new actions, for example, or adding links between existing actions. And so what you do generally is that you start from a plan that only contains the objectives of the mission, and you search for a way to build a plan which is complete. So we say that the plan has no flow, meaning that the plan will be executable by the system. I have a small example to show how this works. I'm sorry. So here you have a simple example where you have so two robots in cell 2-2, and they must explore the cell 1-2 and the cell 2-1. And so the planning algorithm starts from a plan where you have only this kind of empty plan where you know the initial state and you know the goal. And in this plan, there are flows. So one flow is that the cell 2-1 is not explored, and the other flow is that the cell 1-2 is not explored. So these flows correspond to preconditions of the goals that are not satisfied. And then you try to modify the plan to satisfy these flows. The first way would be to add a new task in the plan. So for example, to explore the cell 2-1, we add a task to observe the zone. And when creating this new plan, we have new flows, and the new flows are that the precondition of the new tasks are not fulfilled, and the task is an abstract task, so we will have to decompose it. And again, we will try to solve the flows iteratively in the process. And for this abstract task, we'll decompose the tasks in simple primitive tasks. What we cannot see in this figure is that, of course, it's expanding a search space. So you have some branches in this space. So you may have several actions that you can add to solve an open link, for example, or several ways to decompose an abstract task into primitive tasks. So that's the general concept of hybrid planning. It's a standard POP algorithms with hierarchical decompositions. And what we have done specifically in the HiPOP algorithms is that we developed a new planner, which is a domain independent planner. So we can solve any kind of problems if you give the PDDL-like description of the problem. It accepts both goal states and task states. So in the example I've shown just before, it was a goal state to explore a zone, but you also may say that you want a task to be fulfilled, and this task will be decomposed. It solves classical planning problems, temporal problems with derivative actions, hierarchical task networks, partially ordered hierarchical task networks, and a specific kind of a problem, which is HTN with task insertion, meaning that you in addition to the decomposition of the task, you can also add new tasks that were not designed or specified by the user. I would just like to emphasize that HTN with task insertion is a very hard problem to solve. The plan existence problem is even undecidable in the general case. So it's a very complicated problem, theoretical problem. And in the initial HiPOP contribution, we made a lot of improvements on standard heuristics. So we tried to use standard heuristics used in planning, like delayed relaxation based heuristics, to specifically solve the HTN problem with task insertion. So this work was initially done by Patrick, which was one of my students at this time. And recently we have made a new implementation of the HiPOP algorithms using Python, where we updated all the grading and heuristics computation using more modern techniques. Currently, the new version is under competition in the ICAPS planning competition in the hierarchical track. In this competition, we only solve pure HTN problems, though without task insertion. And among the participants, only 2 other planners can solve partially ordered HN problems in addition to HiPop. So it's a problem which is not so much dealt with in the robotics and planning community. And as soon as the results of the competition are made public, we will also release an open source version of the Python version of HiPop. So we used HiPop to compute the initial plan that you've seen in the movie, where we allocate the task to the robots to navigate to the observation points and to make the observations. And in this plan, there was also some tasks for communication, so that the robots could report what they observed to the operator using other robots as relays of communication. That was in the initial plan. At execution, we will have to repair the plan because we may have some failures, like a robot not maybe out of battery, so it cannot fulfill the mission at all, or maybe a sensor is broken, so it can make some observations, but not all the observations. And in that situation, we have to change the plan and adapt the plan to the situation. So we made a first version where we used the HiPop algorithms to replan all the plan, to repair, sorry, all the plan for all the team. And the idea was to reuse the same algorithms. The algorithm has no modification at all. Just we change the initial plan that we give to the algorithm. So if I go back to the animation here, what you can see is that in initial planning, we just give a plan with the goal to achieve. But if I give the plan, for example, this plan to the planner as an initial plan, and I say, okay, you have this plan to solve, and one thing has failed, so I removed an action in this plan, for example. For the planner, it's the same behavior, the same computation as in the initial planning part. So we just with the change, the initial plan we give to the planner. And with this simple idea, we implemented an iterative process where when there is a failure, first we take the plan and we remove the actions which are directly impacted by the failure. So for example, if a robot is out of service, we remove all the actions the robot has not performed yet. If a sensor is failing, we remove only the actions related to the sensor. So once we have removed these actions, we try to find a new plan, and we give the new plan to HiPop, and we limit the search time to with a timeout. And if there is no plan found, then we remove more actions. So we try to remove the actions that were linked to the actions that we removed before, and we iterate again and again. What we do more specifically is that we never remove the past or ongoing actions. So what has been done or what is ongoing stays in the plan. So there is no way to remove them. So we have defined this iterative process based on HiPop, and then we have used this iterative process in the distributed architecture we have deployed in the system. So the idea is that as we have some uncertainty about communications, we cannot rely on a centralized planner. So we have to give to the robots the capability to replan and adapt their plan by themselves. And the way it is implemented is that when there is a failure and that the robot detects the failure, so it can detect that his battery is out or his sensor is broken, then it will start a repair process. And when it starts its repair process, it becomes the master of the repair. Then when it becomes the master, it will contact all the robots that can communicate with it. And it will decide to repair for the bunch of robots that are in communication. So we use exactly the same repair process I presented in the slide before. So it's an iterative process where we remove actions from the plan, try to solve this plan which is not complete. And if it does not work, we remove more and more action. In case of partial communication, we do a specific thing in addition, is that we lock the actions from the robots that we cannot contact. The robots that are not in communication, we cannot remove their actions. Then when the communication is reestablished, we try to merge the plan. So most of the time it will works quite easily because plan merging is a very natural construct in the POC paradigm. So if you have two plans and you try to merge them, most of the time it will work. The only specific case is that if both subteams have tried to modify the plan, and then only a subpart, which is a kind of intersection of the subteams, or not the whole team, but the small part, modifies again one of the two plans. So it's a very um, specific case that does not happen often in practice. And if we see that the plans cannot be merged easily, we can at this moment try to replan again the new plan for the whole team. But in most of the cases, it's quite easy to merge the plans if we lock the actions from the uncontactable robots, including the communication actions, where the robots must synchronize themselves. And so that's what you've seen in the movie. So in the experiment, so we have deployed this architecture with a decentralized repair process with partial communication. And we have conducted a set of experiments, something like half a day with only the recharging or battery change break during the experiments. And we tried a lot of situations with artificially breaking either a sensor or a robot, or removing 1, 2, 3 robots, limiting the communication. So we had some actual communication limitations due to the size of the environment, which is something like 1 kilometer square. And we also artificially limited the communication to test whether we are robust to more constrained communication environments. What we are doing now is trying to cope with more complex missions. So in the missions I showed in the movie, the mission is very simple in a sense, because there are only one type of task, which is observe points of interest. And the robots were just navigating in the environment to observe these tasks. Yet we manage failures and repairs, but there is no much diversity in the tasks to allocate. So now we are solving very more complex missions, as depicted in the figure on the right, where robots can be used to either protect some areas and detect some intruders, map some building, for example, so go inside some building and take some picture, follow a human, for example, to help him to carry objects. And more specifically, in this new task, we have some joint tasks that need a lot of synchronization between the robots, like collaborative mapping. So two robots have to map a building, but they have to exchange some data all along the task. So during the task, we have to ensure the communication, possibly by assigning a new robot as a communication relay. We also have joint tasks like drone delivery. So a drone can be carried by a ground robot, as like the ground robot you can see on the bottom right of the slide. So it will carry the drone and deliver the drone where the drone must do its task. So we have again to synchronize how the robots behave together. And moreover, we like to allow more intervention from the operator, like designing new objectives, allocating specifically a task to a robot during the execution, so that we will have to adapt the plan to this manual allocation. And finally, in the complete architecture that we develop, we also need to interface with more procedural behaviors, which has been programmed in behavior trees. So we have some parts of the repair procedures that are encoded in procedural behaviors. And we have to integrate the mechanism of repair of HiPub with these behaviors. And for that, we kept the idea of a hierarchical decomposition of the decision making, and we have designed a hierarchical architecture where we have HiPub at the top and procedural behaviors below. And the hot topics that we are investigating now are just on the slide before. We should have done some experiment in spring. Of course, you imagine that it wasn't possible, so all the experiments have been postponed to next spring. So I hope next year we will have new videos and new papers to illustrate this work. We are also investigating new way of having the operator involved in the decision-making process, not just adding new tasks and taking control of robots, but also involve the operator within the decision-making process through two main items. The first one is interactive planning. So we would like the operator to be able to help the algorithms, help the decision process in solving the system or adapting to the system. And one typical application would be that the operator could help in deciding which action to remove when we repair the plan. So instead of just removing the action directly impacted by the failure and following the links between the actions, maybe there are some operational knowledge that we can integrate where the operator could say that if we remove these other actions, which are not really linked according to the plan with the previous one, maybe we will have a better chance to find a new solution. So we would like to give the opportunity to at the operator to intervene in the planning process. And second, a very quite a famous topic now is plan explainability. So the objective is to be able to explain why some actions are in the plan or why some actions are planned before others in the plan we have built so far. The good news is that POP and HCN planning paradigms are already quite used, and we can find some work already that use this paradigm specifically for interactivity and explainability of plans. So we have some ways of doing this, and it's yeah, a good way to start. And finally, we will try to solve new kind of applications. So we have also a project that starts on deploying fleets of submarine robots in order to inspect the borders of a port, for example, or sea borders of a country. So we'll try to use the same kind of distributed architecture with hybrid planning inside. But in that case, as you may imagine, we have even more significant communication constraints to manage. And just to mention, we also are involved in a student project, so which is a part of the IGLUNA project. So IGLUNA is a project funded by the European Space Agency, which tries to involve student teams in Europe to propose new ideas for space habitats. And so a student team from Politecnico di Torino and ISAE Superiore in Toulouse have proposed to use two robot teams, so a ground robot and then aerial robots, to help for remote operation in space. Specifically, you can imagine in the moon. It's also a hot topic at this moment. And they plan to use hierarchical and hybrid planning to program the missions of these robots. So I've done. So if you have some question, I will be happy to answer.